Hello and welcome to part 2 of this video where we're going to have a look at some of the techniques used in building the wings for this vulture character. If you haven't seen part 1, I do recommend you check that out first, as we will be building on some of the concepts discussed in that video, so it's better if you're familiar with those ideas first. I'll put a link to that video in the description for this one, as well as the files that you'll need to get started with this second part. I'll also link to the final file, which will be wherever we get up to today. Hopefully that's going to include some nice techniques for getting these overlapping feather groups and also getting this cover piece of geometry to wrap nicely with the wing as it deforms. And that's the idea. Let's hope we get there. Okay, so let's start by taking a quick look at the file that we're going to use as our beginning point for this part of the tutorial. It's more or less identical to the file that we finished up the last part with. The only real difference being that I've imported this extra piece of geometry here, wing cover LGO, and this is just a piece that wraps over the top of our feathers and kind of hides there where they join into the wing. It should give us a nice rounded leading edge for the wing and just help it blend into the body slightly. By no means anatomically correct, but for the stylized character I was building, this was a good solution for this part of the wing. I'm going to hide that for now, because the first thing we're going to look at is a method to group these feathers into a distinct unit so that we can decide where we want them to start and finish along the surface of the wing, and also vary their size as they travel along the surface, so that we can start to build up layers of distinct feather groups that have different start and end points, different scales, and also a little offset so that they don't overlap each other and we get that nice layering effect. So let's jump into a geometry nodes layout. This is the tree we ended up with at the end of the last tutorial. I've added an extra little frame in here just to keep things nice and clear. That's the part that restores the feathers back to their original shape once they're aligned to the curves. And what we want to do is to select all of these groups in the middle and hit Ctrl G. What that's going to do is make us a node group. We can pop in and out of the node group using Ctrl Tab to go back up to our main node layout, and Tab with the group selected to go back inside it. So we can immediately see this is a lot easier to look at now. Let's just bring these guys back a little bit. And we're going to give this one a name. I'm going to call it primary feathers. And if we pop back into there, we can start to give some inputs to this group that will allow us to control how these feathers are laid out. The first thing we want to do is to control our original curve line, which, if you remember, runs along the top of this 0 to 1 space. Now our feathers are grown off this curve, so if we take this start vertex on the curve and move it this way, our feathers will start growing from that point instead, like that. And the same at the end. We move this end point back, the feathers won't reach right to the end of the wing, which is great. So all we need to do is expose the X values of our start and end coordinates for our original curve to this node group, and we'll be able to control that on a group by group basis. So what we will need to do is, because this is a vector and we only want to control one channel of it, we'll use a combine XYZ node. We want to match these up initially, so put 1 in Y, that's this guy, duplicate that 1 in X and Y into there, and now we want these X's to be available from the outside of the group. So let's hit N to bring up the node group properties, and we can rename these inputs. This will be start, and this one end. So now if we hop outside the node group for a second, we can see we've got those parameters available now, and we can control this from here. Okay, next let's look at a method to scale the feathers as they go from the start of the curve to the end of the curve. And the scale is controlled in two different places. The first attribute we need to look at is where we move the feathers to the curves, and this multiply value here is what controls the length of the feathers. And then over where we rebuild them to their original shape, we have this scale value here which controls the X and the Z coordinates, so the fatness of the feathers. So if we drop down a new group input, I'm going to add a new input clicking this plus button here. I'll call this one scale start, and the second one scale end. And what we want to do is vary the scale based on how far along the wing we are. So I'm going to drop down a map range node, and our start, so where the feathers begin to grow from, I'm going to put that into the from minimum, end into from maximum, scale start into the to minimum, and scale end into to maximum. So for this value node, what we want is to have this input vary from 0 to 1 as we count up to our total number of feathers. We have the feather index stored already as an attribute. What we don't currently have access to is a control for the number of feathers. We've just been manually controlling that via this resample curve node. So first job is to expose this to our node group so that we can control that from outside the group. And we're going to need to remap this value such that it goes from 0 to 1 as we travel along the wing. So let's drop down another map range node, and our count is going to go into our from maximum. The value is going to be our feather index, so that counts up as we go along the wing. And then we want to match the output range for this node to the input range on this map range node here. So we're going to take the same start and end values and pump them into the to min and to max. The result of this map range becomes our input value for this one, and then the result of this guy becomes our multiplier here for the length of our feathers. Now these are going to jump to 0 because we haven't currently set any values outside of the node group. So let's quickly go and change that. Control tab to jump back up a level, and we want our scale start and our scale end not to be 0, obviously. If we set those both to 0.35, which is what we had before, we should restore our original state. But now if we play with these guys, we should be able to vary the length of those feathers as they travel along the distance of the wing, and that should also respect wherever we set our start and end points to be for that group of feathers. And we can now vary how many feathers we have in this particular layer. Jump back into here, and we're going to want to set up the same value for our width of our feathers as we have on the length, all being driven from the same input. Just check that still works. There we go. So now as they're getting shorter, they're also getting narrower. So there's just one more level of control that I'd like to add to this group before we move on, and that is the ability to push or pull the group as a whole either towards or away from the surface of the wing. So we're creating an offset that will allow us to have multiple overlapping groups of feathers that don't interfere with one another. So let's hop back into this node group, and what we want to do is, after we've restored the feather back to its original shape, we want to add another offset based on the normal of our underlying wing surface. Let's just give ourselves a little bit more room here. So if we drop down a vector math add node, we'll duplicate our group input node because we need to add another parameter to this. This one's going to be a float attribute, normal offset. And what we want to do is multiply the normals by this normal offset and add it back to our original vectors. Take this value here. We're going to scale it by the normal offset, add this into here. Nothing should happen because we haven't set any values outside the node group yet. Let's just go and make sure that's working. As we increase and decrease this value, the feathers move towards or away from the surface. These normal offset values, we need them to be quite small so that the wing doesn't become too bulky. And I like to vary the normal offset along the length of the feather. So as you get towards the end, it's pushed out slightly more. And as we come towards where it inserts into the wing, they become slightly tighter packed. And the way we can do that is to reuse this feather position attribute, which we originally stored. And as we travel along the Y parameter of the feather, we can use that as a multiplier for this value. So if we drop down yet another scale vector, and we're going to use for the scale this Y coordinate of the feather. So now when we add a value to this, you can see that the roots stay still, but the ends of the feathers are what are getting pushed away. And we could remap this again if we were to drop down a map range node there. We could add some value into here in the to minimum so that when we do manipulate this, the roots don't stay completely still. So let's have a quick look at using this node group that we've built to create an extra layer of feathers. Let's bring back the cover geo so we can get a better idea of the shape that we're working with. And hop outside our node group and start adding some values. I'm just going to unhide the armature for a second as well so that I can see where the splits would be naturally in this layout. So I'm going to shift the start of these primary feathers along, make them slightly larger at the start, something like that. I might want a few less feathers in there now that we've compressed them together. And then what I'm going to do, and this is the beauty of all the work we've done, is that I can now duplicate this node group, give it a different name just for clarity, put our value in, add it into the join geometry. At the moment this doesn't look any different because the settings are all the same, but what we can now do is bring this back to 0 so they start right from the beginning. Maybe increase the start scale and decrease the end scale a little bit so we get this overlap. And now I'm going to add a small amount of normal offset to this group so that they sit outside those ones. Hide the armature and let's just see what that looks like. Hide that cover for a second as well. We might need a few more feathers on the second group because we're spacing them out more. But yeah, that's pretty much what I did on the vulture character to create those layered effects of the feathers stacking on top of each other. Okay, so in the next section, what we're going to do is look at how to deform this cover geometry so that we don't get any collisions between the feathers and this outer piece. And what I was finding was, because we're basing the feather orientation on a very low resolution base mesh, which we then subdivide to get that really nice smooth curve when it deforms. When I tried to have this piece follow along with regular skin weights, I wasn't able to get those nice smooth transitions, or rather I was, but I would lose volume, which meant that the feathers would poke through here and there. So what I wanted to do was find a way to drive the deformation of this cover piece using that same low resolution base mesh. And that's what we're going to look at doing next with geometry nodes. So I'm going to temporarily hide our feathers geometry and our armature and just bring back the low resolution base mesh for now. And the approach we're going to take for this is slightly similar to how we laid out the feathers, but with a couple of key differences, because we're not actually generating this geometry based off this underlying structure. This is a pre-existing model that we just want to deform based on this. So the first job is we're going to store the closest point to each of these vertices on this base mesh, and the piece of information we need is the UV coordinates at that point. So for this point here, we're going to look at the underlying mesh and say, okay, the nearest point on the mesh might be here. What is the UV coordinate at that point? So we're going to store not only the UV coordinate but the offset between that point and this point as a vector, x, y, z. What we can then do is when this wing deforms into a pose, we can say, right, where was that point? Because we know the UV, so we can say here's the UV, what's the new location of this point? And then we can go back to our original vertex and reapply that offset, but using this new point instead of the original one. So we're pushing the position of this vertex based on the deformation of this UV sample point. I hope that makes sense. And it's not just a simple question of adding the offset to that new point, because what we haven't stored is any orientation information. So we're going to have to rebuild that using the normals of this surface and a couple of other vectors which we're going to have to derive. Anyway, that's the theory. Let's get started. So we're going to a geometry nodes layout, add a new geometry nodes node tree to our cover geo, and we'll call this wrap deformer, because that's essentially what we're doing. We're wrapping this surface to this surface. Okay, so the first thing we want to do is find the closest point on this base mesh and store its UV coordinates and our offset. And this is where we're going to run into our first problem, which is if we use the actual surface that's going to deform, then our original closest point is going to change based on that deformation. So what we're actually going to need to do is make a duplicate of this wing surface. And we're going to rename this to something like wing reference. Going to remove the armature modifier so that it doesn't deform anymore. We're going to keep the subdivision so that the topology remains the same between these two surfaces. We're going to hide that one off for a minute, and then in our wing cover geometry nodes we want to drag this in as an object info. So we're going to drop down a sample nearest surface. The geometry that we want to sample from is our reference The information that we want is going to be a vector, and the value that we want to sample is going to be a named attribute called UV map. That's going to go into the value. We also are going to need another sample point, which is going to give us the basis for one of our vectors that I mentioned when we need to reconstruct that orientation. So what we want to do is sample not only the UV that's closest to these verts, but we want another sample which is offset on the z-axis ever so slightly. So the difference between those 2 points is going to give us one of our vectors for our reconstruction. So we'll have another sample nearest, same inputs, but this time instead of leaving this as the default position of this vertex, we want to offset that position down slightly in z. Now here's where a little caveat needs to be mentioned. I've deliberately built this wing model so that it's aligned vertically. You know, it's all on one plane such that the Z is up and down, and that allows us to just offset these points down a little bit to take our second sample. If this was a more complex underlying surface, or if it was aligned in a different plane, we might not be able to rely on just a simple offset down in the z-axis. So just keep that in mind if you're building a wing or using this technique on a more complicated surface. So instead of the default position, we're going to drop down a position node, but we're going to subtract a small amount in z from this. Start with maybe 0.1, and we'll put this into the sample position instead. So now we have 2 UV map samples, one closest to the vertex and a second one offset down slightly. We're also going to need to store that offset in position between the closest UV sample and the vertex itself. So let's just start to organize this into a little frame. This one's going to be sample initial UVs. We want to use our reference base mesh again. We're going to need another sample nearest surface. This time the value that we want is going to be the position of the closest point, and we want to subtract the position of that closest point from the position of our vertex. So we subtract that from the position of our vertex, like that. And then we need to store this for use later. We'll use our store named attribute. We'll call this position offset. And let's just frame that up for organization as well. So now we're going to need to basically rebuild these offsets to each vertex based on the deformed surface. We're going to do that one axis at a time and then add them all up at the end. So I've got a pose stored where the wing's deformed. So what we need to do is drag in our deformed wing surface now. So this was the undeformed reference surface. This one's the actual wing surface that's driving the feathers, the one that's connected to the armature. And we're going to need to start sampling some values from this surface. Now we've stored these UV coordinates for each point, the nearest UV coordinate. So we can now sample the UV surface of our deformed base mesh. The source UV map is going to be the same as this one. It's called UV map. The sample UV is going to be this one, the closest one to our vertex, and the value that we're interested in for this first vector is going to be the normal. We want the normal of this deformed surface at this UV sample point. We're going to do these offsets in order of complexity, I guess. I think the Y is going to be the easiest to calculate because it's going to be a simple multiplier of the surface normal at this sample point. So we have our offset. We stored that as position offset up here. So if we drop down a named attribute node, it's a vector, pos offset. So if we separate our positional offset, because we just want to work with the Y component for now, what we can do is scale the normal vector that we just derived by this Y component. So whatever length our original Y offset was, we're going to push along the wing normal by that distance. And that is going to form the Y axis of our offset. Okay, let's move on to the next axis. We'll work on the Z next. Now, the Z axis needs to be perpendicular to the normal, and we want it to run vertically aligned to this surface, which is why we sampled that extra UV coordinate, which sits directly below the one we just used in our normal. So if we take the position of this sample and the position of this sample, subtract them from one another. That will give us a vector that we can use for our z-axis. So let's drop down another sample UV surface. We want our deformed geometry as the mesh. The source UV map will be the same as this one. The value this time is not the normal. We want the position of that sample point. And the sample UV is going to be the same as this one. Try and keep some of these noodles slightly tidier. There we go. This is going to give us the position of the UV sample point closest to each vertex. Now we want to extract the position from this offset UV sample point. So we'll take yet another one of these. Same geometry. Again, the value is position. Same UV map. And the sample UV in this case will be this offset UV that we stored. So if we subtract these vectors from one another, this should now give us a vertically aligned z-axis that we can multiply by the z component of our original offset. Let's just duplicate that down. Z offset is the scale. This one is the vector rather. Okay, that just leaves the x-axis of our offset to deal with, which we want to be perpendicular to both the normal and the axis that we just derived. And if you remember from part 1, the operation we can use to give us that third vector, which is parallel to two input vectors, is the cross product. So let's drop down a vector math node, set this to cross product. Input 1 is this normal. Input 2 is going to be this vector here, but we do want to normalize that vector first because the distance between these two sample points, we can't guarantee that's going to be 1. And we want both of the inputs to our cross product to be normalized to make sure we get a normalized vector coming out. So this one here is going to form the x component of our offset vector. So let's duplicate this one more time. We want to scale by the x component, and this is going to be our input vector. So we now have x, y, z, and we just need to add those all together. These two first, and then add the z. So this is going to be our final offset result in the space of the deformed wing. And of course, we're going to need to add the actual position of the closest UV sample point, because this is just the offset from that point. We also need to move that offset into the position that corresponds to the wing. So position of the original UV sample point is this one. Take this value up here, and this should give us our final deformed position. Let's add that in. Okay, we've got a problem here, and that is because we never actually piped our original geometry through the store named attribute node here, which means we never actually stored those offsets to begin with. Okay, that looks promising. We've got one or two issues. It looks like this has been brought down slightly compared to its original position. You can check this by temporarily disabling the modifier. Okay, it's only those top verts that seem to be having a problem. Let's check when it's actually deformed. Seems to be working well apart from that top row. Okay, I think I've figured out the problem. Basically, where we've subtracted the offset sample point from the closest sample point to get our vertical vector, we've normalized it before making our cross product, but we're using the unnormalized version to create our offset, where we actually need to use the normalized vector itself. So we plug that in instead. That's going to create the opposite problem. So we just need to swap a couple of inputs around. We need to swap the order of subtraction here. That will fix the z offset, but it will create a problem with the x offset. So we also need to swap the order of inputs to our cross product calculation, and that should pop things back just where we want them. So as we can see, that wing geometry, the cover geometry, is now deforming nicely with our base surface. If we hide that and bring back our feathers, you can see that we're not getting any nasty poke through as we deform the surface. It's all conforming nicely. And we probably want to throw a subdivision surface modifier on top of here just to clean things up even more. But essentially, that's how I did that part of the wing geometry.